Hi everyone. I have a request to make a quick helper video to point you in the right direction on the problem set electric charges and magnetic fields. It's a Schoology assignment. I believe it's in this week's purple folder. Okay. So anyway, I'm going to start with number 10, just because the ones before this are mostly just right-hand rule stuff, right? So I'm going to start with the quantitative stuff. Number 10. And so I'm reading this thing here, and it says that an alpha particle in a magnetic field travels in a circular path. What is the speed of the particle? Well, so what we have to recognize here is that there's something going in a circle, right? So, and in general, forces are required to keep something going in circular motion. We call those centripetal forces, and they're equivalent to mv squared over r. Right? You probably remember that from physics 1, right? To keep something going in a circle, well, if it's more massive, you need more force. If it speeds up, you need much more force, v squared. But to go in a tighter circle, r, you need more force. To go in a bigger circle, you need less force. Okay, that's the centripetal motion, the centripetal force formula, which is really F equals ma, where a is v squared over r, toward the center. Right. Now, we also know that a charged particle in a magnetic field feels a force. And a charged particle in a magnetic field feels a force equivalent to Q times V times B. The charge on the particle times the velocity of the particle times the strength of the magnetic field in Tesla. Okay. Now, so the picture I'm looking at here on this video looks like there's a particle traveling in a B field, and it's being pushed into circular motion because the force is always perpendicular to its velocity. It's always a force, and that's going to result in, as we spoke about the other day, in a central force, a force toward the center of a circle, right? So there is a centripetal force, and it's caused by and equal to the Q times V times B, right? What is the force on this particle in this picture? Well, it's a magnetic force, and what's it equal to? QVB. It's also equal to the force pushing it into that circle. So mv squared over r, the centripetal force, is a magnetic force. Okay, now let's just simplify a little bit. I think this one says what's the speed. Yeah, so we just have to solve for v here, right? I'm going to go ahead and multiply both sides by r and divide by m, and I get v squared is qvbr over m. But let's divide both sides by v, because I got a v here and a v squared here, so let's do that. So in general, the speed of the particle will be q r b over m. Okay, so there's not the answer to number 10 here, but there's the formula for number 10, and you have all these quantities. You have the charge on the alpha particle, you have the radius of curvature, be sure to put that into meters. You have the strength of the B field, it's in Teslas, good. And you've got the mass of the particle in kilograms. So check, there's number 10, that'll get you the velocity, right? So let's just say, let's say V equals V of the alpha particle. I'm not going to solve it for you. You get the number. I'm just going to call it V alpha, right? It's got some velocity, V times alpha. So that'll get you the answer to that one. Progressing to the next one, number 11. What is the KE in electron volts? Well, in general, the kinetic energy, I would just do it the old-fashioned way because we have all this stuff, is mv squared, 1/2 mv squared. So here's number 11. The kinetic energy is going to be 1/2 mv squared. Now, but that'll give you the answer in joules. Right? That'll be in joules. So how do we go from joules to EVs? Okay, so for number 11, what I would do is I would just say, well, the kinetic energy is 1/2 mv squared, right? And so you'll notice, well, we have V, I think we called it V alpha. Right? From number 10, we have some quantity, velocity. You solved it, you have a number, I'm just calling it V alpha, the velocity of the alpha particle. So I've got the velocity, I showed you how to get it for number 10. And so to get the kinetic energy, it's just 1/2 the mass, which is given, and times the v squared, which you solved in number 10. Now, your answer will pop out in joules. Now, how do you turn joules to EVs? Well, let's take a quick look at what an EV is. Right? So if we just have these, consider this, we've done this derivation before, but let's just remind ourselves of it. What if I have I hook this to a positive end of a battery, and I hook this metal plate to a negative end of a battery, and so I establish an electric field inside of here where the field goes from positive to negative. Right? So that's the E field. Now, if I want to move an electron from here to here, well, let's say this is the 0 volt position, and that's 1 volt. So it's just 1 volt of difference here. 1 volt of difference. And I'm going to move an electron from here right up to there. Right? I'm going to have to do work, right? Because there's a force interaction here. It's attracted to this plate, and it's repelled from that plate. So I have to push that thing in order to get it to go up the gradient, to go up the voltage gradient. So how much work do I have to do? Well, I don't know, but let's pull out our definition of voltage. We have a definition of voltage, which is energy, electrical potential energy per charge. And the change in something's EPE, or any energy, really, is equal to the work that's done on it. So we could write this as work done per charge. And then we could say, well, therefore, the EPE, or the work, is V times Q. The work that I do on it is going to be equal to the energy that I give it, which is going to be equal to V times Q. Okay? So in order to move an electron up, how much work do I have, up 1 volt, how much work do I have to do? Well, I have to do the charge on the electron times the voltage, which is just 1. Right? So the charge on the electron is 1.6 Q times V. 1.6 E negative 19 coulombs times 1 volt. So how much work do I have to do to bring an electron through 1 volt of potential difference, to do work to raise an electron up to the 1 volt mark? Well, 1.6 E negative 19 times 1. So I have to do 1.6 times 10 to the negative 19, joules of work. Now, that's a tiny, tiny, tiny number. And so we give that a special name. We call that 1, electron volt. So what's an electron volt? It's a very small number of joules, 1.6 E negative 19 joules. So when you run this equation for number 11, what is the kinetic energy in electron volts? When you run this equation, you're going to get it in joules, right? But then just use this conversion factor, that 1 EV is 1.6 E negative 19 joules, and that'll convert it into EVs. For example, I don't know, if you come up, I'm just going to make up something silly. Oh, it's got 0.2 joules. Well, how many EVs is 0.2 joules? Well, let's see. 1.6 E negative 19 joules is 1 EV. Right? So I would just divide 0.2 by that number, and I would get a value. Okay, that's how you turn KE into EVs. All right, let's carry on here. That was number 11. Through what potential difference must the particle be accelerated in order to give it this KE? Okay, so you're going to have a number here. You're going to have a number. You're going to have an actual number, right? So you're going to have some amount of kinetic energy, right? You're going to have some amount of kinetic energy, right? And you want to, and so this is a given, so you'll have that, right? And you want voltage. Through what potential difference must it be accelerated? And it's an alpha particle, and you're given, I don't know, you have its mass, you have its charge. What else do we have? We have its mass, we have its charge, we have the radius of curvature. We don't need that here, right? So I need voltage, and I've got KE, mass, and charge. I don't think mass is going to play into it. But wait, let's look up here. Sorry, I've got KE, I've got mass, I've got charge for this question. I'm wondering about V, voltage, potential difference. Well, let's go right up here. EPE per charge, or work done per charge, or in general, just the amount of energy per charge. Right? So what potential difference, where are we at? Number 12 here? What potential difference? V is going to be, in this case, the energy per charge will be the kinetic energy per charge. Okay? And, well, there's the voltage, right? And there's the KE per charge. Okay? So this one, let me think for a second. You can do, yeah, I would do joules per coulomb. Right? You'll get the voltage there. Okay, that's how you get the potential difference for number 12. What's this one here? Same current parallel to each other, 10 centimeters apart, of 10 amps of current flowing through them. Points A and C are 5, yada, yada. What is the B field strength at point C due to only the wire on the right? So this wire is creating a magnetic field at point C. Let me switch my papers here. Okay, and the formula for the magnetic field next to or near a current carrying wire is mu naught times the current divided by 2 pi r. Okay, well, mu naught is a number, which is 4 pi e negative 7, 4 pi times 10 to the negative 7. Those are Teslas times meters. I kind of forget the units. I'd have to look it up. I'm not going to slow down to look up the units. There are units there. They should go there. I'm being quick and lazy here. The current, I have the current. I have 10 amps of current. And then down here I've got 2 pi times the distance it is from the wire. Well, let's see. Points A and C are 5 centimeters from the wires, and the wire on the right. Yeah. So 5 centimeters. 0.05 meters. That will give you the B field at the point C right here. Right? And it's going to be some number, right? I'm not going to sit here and pound the calculator for you. You guys are good at that, right? So you're going to have some number, and that's the answer to this one. The B field strength and direction at point C due to only the wire on the right. Okay, and what's the direction? Is it into the page or out of the page? Use your right hand, put your thumb in the direction of the current, and your wrapped fingers, if you could wrap them around this wire with your thumb in the direction of the current, you're going to see that the B field over here is either into or out of the page. And I want you to tell me. Okay? And that'll give you the answer to this one, 13. Number 14. How about point C due only to the wire on the left? Well, it's the exact same formula, except here's the wire on the left, except it's 5, 10, 15 centimeters from the wire on the left, right? So that will just turn into, for number, where are we at here, 13? Sorry, 14. I think I misspoke about the earlier one, but whatever. We're on this one here, number 14. And here the distance from the wire, the left wire, is greater. So that becomes a 0.15 meters. And this is number 14. For number 14, it's the same formula, but with, the wire the point is 15 centimeters from that wire and 5 centimeters from that wire. 5, 10, 15, yeah, okay. And what about the direction? Use your right hand. Current's going this way, and the field is weaker for sure, but is it up or down or into the paper, out of the paper? What is it? What is it, right? So use your right hand to figure that out. And let's go to the next one. Oh, the vector sum at point C. Well, so I'm just going to make up some numbers here because, I didn't run the numbers. So I'm just going to make something up. Let's say I ran this number. I'm just going to make up some unreasonable number. And I got 5 Teslas. And I got, whatever, towards me. 5 Teslas towards me for that one. And then let's say I did this one here, and I got yada, yada, yada. Well, it's going to be, right, it's going to be the same numbers, except it's going to be, 3 times less, right? So whatever 5 over 3 is, right, this one's going to be 5/3 Tesla. And it's going to be in the other direction. Now, I'm not sure if these are right or wrong. These certainly are not right? But my point is this, right? What's 5/3? Let's just call that a number. I don't know. It's like 1.7, 1.67 or so. Let's say this one's 1.67 Teslas away from us. Well, then I've got so at that point C, which is labeled at that point C, I've got two fields. I've got I'm going to use my numbers. I've got a 5 Tesla field towards me. I've got a 1.67 Tesla field away from me. And so the net field would be, well, which one's bigger? That one is. So it's going to be towards me. And it's going to be 5 minus 1.67, which is like, what is that, 3.3-ish, 3.33? Yeah. So I would say, okay, the net field, it's basically the sum of the B fields. The sum of the B fields is towards me with 3.33 Teslas. You just do the same thing you would do for adding any forces, right? If I said little Johnny pulls the cart that way with 10 newtons, and big old Sally pulls it this way with 15 newtons, and I said, well, what's the sum of the forces? And you would say, oh, well, to the left with 5. Big old Sally wins with 5 newtons, right? So same thing here, except it's sort of into the page and out of the page, and it's not so simple anymore. It's just pushes and pulls. I mean, it is, but it's a field, so it's harder, right? It's harder, but it's the same idea. It's the same idea. Okay, the vector sum of the B fields. And then what do we have here? This might be the last one. Yeah, it is. So this was 15, the vector sum, right? Number 16 is, a circuit's constructed, okay, so same setup. What is the net force per length on the left wire and the right wire? Well, let's not forget Newton's third law here, right? If you push on a me, I push it back on a you, igual y opuesto. Or as it's commonly stated, for all action forces, there are equal and opposite reaction forces. So, if we find this wire's pushing on that one with 10 newtons, well, guess what? That wire's pushing back on that one with 10 newtons. Let's just determine what the number is, or let me show you how to, and then how to deal with the direction. Okay, well, let's start here. So let me just separate that out by doing that. And say, in general, well, why is there a force? Well, because this wire has a magnetic field around it. And then I've got a current over here in this one's magnetic field. And around this wire, there's a magnetic field. And in that magnetic field is this current. So there's a force on these charged particles moving in that one's magnetic field, and there's a force on these charged particles moving within that one's magnetic field. So what are these? These are wires and magnetic fields. The force on a wire, a current carrying wire in a magnetic field, is I times L times B. Okay? Now, as we saw up here, the B field created by a current carrying wire is mu naught I times 2 pi r. Right? But let's do this first, because we're looking for force per length. Like for every meter, how much force is there? Well, it's just I times B. Okay? So let's call these wires left and right. I don't know. So the I and the left wire compared times B. What B? Well, the B created by the right wire, right? If we're looking for the force on the left wire, why is there a force? Because it's in a B field created by the right wire. So we're looking for the B of the right wire, which is equal to mu naught I 2 pi r. So the force per length is the current in the left wire times B, created by the other wire, which is mu naught I. Which I? Well, what's this B field created by? By the current in the right wire over 2 pi r. Okay. Now you usually see this written as F per L is I L I R, or usually it's I1, I2, mu naught over 2 pi r. Okay, that's how you find the force on either one of the wires, right? Because the force is going to be, whatever the force is on the left, it's going to be equal to the force on the right, right? Forces occur in pairs. So force per length. Well, I've got the currents. They're both 10 amps, I think. Yeah, they're both 10 amps. That's a number, 4 pi times 10 to the negative 7th. And 2 pi r, well, the r is just the distance between the wires, which is 0.1 meters, 10 centimeters, 0.1 meters. Right? So you've got all, you just plug the numbers in and you've got F per L here. Now, what is the direction? So the forces are going to be the same on each of them, but what's the direction on the left wire or the right wire? What, so you've got these fields, and let's look at it this way. Let's look at it this way. Here's the wire on the left, and the current is, let's switch colors here. The current is that way. And the wire on the right, the current is the other way. The current is this way. Let's zoom in on those wires to take a closer look and figure out which way the force is. Now that we know the force per length is going to be, well, mu naught times current 1 times current 2 over 2 pi r. So there's the quantity of the force, but what's the direction? Well, for the direction we employ the right-hand rule, which tells us the direction of the magnetic field around a current-carrying wire. So the wire on the right, the current is up, and wrapped fingers would go into the page on this side, and they would come out of the page on this side. Okay? And then let's do it for the other wire too. The other wire, the current is down, so it's into the page on the left side of this wire, into the page, into the page on this side, and out of the page on this side. So what we have here, if you look at, so some people just commit it to memory. When the wires have currents in opposite directions, it's a repulsive force, and when they have currents in the same direction, it's an attractive force. But I, instead of just remembering, I'd rather be able to figure it out from first principles, and so that's what I'm doing here. And if you see, what we have here is this wire and this wire both have like magnetic poles, or the side of the B field next to each other. And as you know, like poles repel, and unlike poles attract. So the forces on these two wires are going to be mutually repulsive. Right? This wire will be pushed that way. It's like two magnets, like two south sides or two north sides of a magnet facing each other. Right? Two like poles of a magnet facing each other. The forces are going to push the wires apart. And super quickly, let's just convince ourselves that if the wires had current in the same direction, which they don't, but if they did, let's see if it's attractive. I mean, I think we know the answer, but let's work it out. Right? So let's say the current was up in both of them. Current is up in both of them. Well, then both B fields, so both B fields are into the page on the right side, right-hand rule, number 1. Right, so both B fields are into the page on the right side of the wire. I guess I'm doing B in green, hold on. Both B fields are into the page on the right side of the wire, right? Wrapped fingers around the wire, they're coming out, the fingers are coming out at you on the left side of each wire. So boom, boom, boom. That's the current coming towards you. Oh, sorry, that's the B field coming towards you. And on this wire, here's the B field coming towards you on this side. So when the currents are in the same direction, you get oppositely, you get opposed B fields in between the wires, opposed magnetic fields, which attract each other. Right? So when the current is in the same direction, the forces are attractive. And when the currents are in opposite directions, the forces are repulsive. Okay? And that's all there is to it. Alrighty then. Have a great day. I'll talk to you soon. Bye.